All right, so our next speaker is Binju from the University of Arkansas, and we'll continue talking a little bit more about the magnetic structure of bismuth ferrite.
Thanks, Chairman. Hello, everyone. Also, I want to thank the organizers for giving me this talk. Today, I want to speak about spin cycloids in multiferroic bismuth ferrites in films. Before I start, I want to first acknowledge my collaborators. For theory, I work with Rohan Blesch at the University of Arkansas, and we collaborate with Bertrand Dupé from Germany. And for experiment, the neutron diffraction measurements on 110 thin film was done by people in Australia, in particular University of New South Wales, the groups of Valenor and Woolwich. And I also want to thank the financial and computational support. So BFO is a very rare room temperature multiferroic. The ground state has this rhombohedral symmetry and with the space group R3C. It has a very large polarization pointing along the 111 direction. It has a very high Curie temperature above 1,000 Kelvin. It also has the antiphase oxygen octahedral tilting along the polarization direction. And its magnetic structure is approximately G-type antiferromagnetic. The new temperature is more than 600 Kelvin. For bulk BFO, it also has this type 1 cycloid with a wavelength of modulation of 62 nanometers propagating along the 1-10 direction. In some previous works, there is a proposed converse spin current model to explain the existence of this spin cycloid. Because of this cross product between Mi and Mj, so this term favors a non-collinear spin order. This C is coupling strength, and Ui is the electric dipole moment on the position I, and Eij is a unit vector connecting position I and j. So in this talk, the question I'm trying to discuss with you is that, can we use this spin current model to understand different magnetic structures in BFO? First, let's see what are the magnetic structures that have been observed in BFO. We already know the bulk BFO has a type 1 cycloid, but this cycloid can be destroyed in many ways. For instance, by applying a strong magnetic field, strong electric field, high pressure, doping, or large epitaxial strain, either compressive or tensile. Under these conditions, there is a transition from the cycloid state to a canted antiferromagnetic state with a weak ferromagnetization. For simplicity in the talk, I'll just call it AFM. There's also a type 2 cycloid in BFO. For instance, in 001-oriented film, under small compressive strain, the type 1 cycloid is stable. But for small tensile strain, the type 2 cycloid with a propagation direction of 1-2 is more stable. The same type of cycloid is also observed in 110-oriented film by our collaborators. And strontium titanate is the substrate. How can we understand these different magnetic configurations? We know that the occurred magnetic structure is the one that minimizes the total energy. And here is the magnetic energies we considered in our effective Hamiltonian. The first term is a long-range dipole-dipole, magnetic dipole-dipole interactions, which is relatively small. And the second term is the short-range exchange interactions, which is strong, and it favors the antiferromagnetic order. And the three terms in the middle are the interactions between the magnetic moments with other degrees of freedom, including the dipoles, the antiferrodistortive tiltings, and the strains. And the next term is the DM interaction, which can cause the spin canting. The last term is the converse spin current model, which is also a DM type interaction. For this last term, the spin current term, we consider both first and second nearest neighbors. We call them C1 terms and C2 terms. In total, there are 6 first nearest neighbors and 12 second nearest neighbors. And the first nearest neighbors have those neighbors in those 1, 0, 0 directions. And for the second nearest neighbors, they are in those 1, 1, 0 directions. In previous works, it has been demonstrated that by only considering the first nearest neighbors or by only considering the second nearest neighbors, we can reproduce the type 1 cycloid propagating along the 1, minus 1, 0 direction. But in this talk, I'll show you that to explain all the magnetic structures in BFO, we may have to consider both the C1 terms and the C2 terms. So what we did is performing Monte Carlo simulations based on the effective Hamiltonian. In the Hamiltonian, we consider not only the magnetic energies I just discussed, also we consider the energy related to the dipoles, the tiltings, and the strain. And we use a supercell size that is 12 by 12 by 12 and 80,000 MC sweeps for convergence. And we study bulk BFO at the temperature of 10 Kelvin. What we did is we varied the C1 and C2, these 2 parameters, independently. C1 is for first nearest neighbor, and C2 is for second. And for each pair of C1 and C2, we find the most stable magnetic structure. And this magnetic structure is determined by performing the Fourier transform. And this is our calculated phase diagram. The x-axis is for C1, and the y-axis is for C2. Each different color represents a magnetic structure, and a different color for different magnetic structures. As you can see, if we keep C2 being 0 and we increase C1, we'll encounter these different phases, starting with AFM, then there's one here, 1, 0, 0 cycloid, then 1, minus 1, 0 cycloid, then 1, 1, 1, minus 1, minus 1 cycloid, then 1, minus 2, 1 cycloid. On the other hand, if we keep C1 being 0 and increase C2, we will have the AFM, then 1, 0, 0 cycloid, 1, minus 1, 0, then there's another one, 2, minus 1, 0, and then 1, minus 2, 1. We also see that for each magnetic configuration, it forms some shapes of bands. And these bands are extending in the direction that with increasing C1 and C2. So not that way, but this way. So just to mention that in total, we have found 6 different types of magnetic structures, including the AFM and type 1 and type 2 cycloids that was observed in experiments before. We also predict 3 new types of cycloids, which were not known before. And the difference between these 3 new types of cycloids compared with the known one is that if we sum up the 3 indices of these 3 numbers, it is an odd number instead of an even number, which means along the propagation direction, these 3 cycloids will be the antiferromagnetic cycloids instead of the ferromagnetic one. Now let's see how we can use the C1 and C2 terms with those 1, 0, 0 neighbors or 1, 1, 1, 0 neighbors that can produce propagation directions in different directions. And so this is the spin current model. And because for the cycloid structure, Mi cross Mj will be either in the same direction or in the opposite direction. So we can rewrite this term as a weight times a unit vector. And then we do this cross dot product, we change it to dot cross product. And then to minimize this energy, the Q vector, which is the propagation vector, is simply the weighted sum of these Eij vectors. And the Eij are for the first neighbors or second neighbors, which are in those 1, 0, 0 or 1, 1, 0 directions. Now let's look at some examples. First, we keep C2 equal to 0 and we increase C1. We first have this AFM phase because in the antiferromagnetic case, Mi cross Mj will be 0. So there's no contribution from any neighbors to this magnetic structure from this term. Then for 100 cyclide, we have two contributions of the same weight because these are the neighbors that is along this 100 direction. And for 1 minus 10 cyclide, we have four contributions of the same weight because this combination of the same weight, it could be plus or minus, that can give us this weighted sum in this Q direction. And then for 1 minus 1 cyclide, we have six contributions of the same weight, and they can give us this Q vector. And the last one is 1 minus 2 cyclide. We still have six contributions, but along the y direction, the weight is doubled. So we have the weighted sum in this Q direction. And that's how it works for the first neighbor terms. And for the second neighbor, C2 terms, if we keep C1 equal to 0 and only change C2, we start with the AFM, no contributions. Then 100 cyclide, 8 contributions of the same weight. So the weighted sum give us this direction. And then 1 minus 10, two more terms, slightly more complicated, but the weighted sum is exactly that. And then 2 minus 10, then 1 minus 21. And then in this, taking this 1 minus 21 as an example, you can see there are different weights from different terms. The opposite ones have the same contribution, so the sum is giving this direction. And if both C1 and C2 are finite, the contribution will simply be a summation of the C1 terms and C2 terms. To understand why each magnetic configuration forms this kind of bands extending with increasing C1 and C2, the reason is that the C1 terms and C2 terms, they are competing. If one energy is positive, the other one will be negative. The reason is because of this Mi cross Mj term, because one is the first nearest neighbor and the other one is second nearest neighbors. And the BFO is the G-type AFM, so that gives opposite sign of this cross product. Then, to estimate the possible values of C1 and C2, we need to consider some experimental facts. Bulk BFO has the type 1 cyclide. Under small tensor strain, there's a type 2 cyclide. Also, under large field of strain, it becomes AFM. Because the energy change, the relative energy change due to the field of strain is relatively small for these different configurations. So it tells us that these three different configurations have to be close to each other on the phase diagram. And the circled region is the only possibility here, which suggests that both C1 and C2 needs to be finite. Also, over here, C1 has a magnitude that is about 1 order of magnitude larger than C2. Another interesting point is that in this region, the highlighted region, we also see a new kind of cyclide which propagates along the 1 minus 1 minus 1 direction. And it will be interesting that this can be checked experimentally later. At the end, I want to show you the scaling behavior of cyclide on 110 film. And these are experimental results with neutron diffraction. So what is found is that the cyclide period increased significantly with thinner film thickness or with the increase in temperature, in particular approaching the new temperature. So this is the thinner thickness and increase in temperature. And the spin current model may offer explanation for this finding because if the polarization decreases with smaller thickness or increase in temperature, then this term becomes weaker. And the weaker of this term means the cycloid period is longer. Because, as you know, the antiferromagnetic order can be understood as a cycloid of infinite length. So to conclude, We have predicted the C1, C2 phase diagram for bismuth spherite. And by comparing with the experiment, it suggests that we need to consider both first and second nearest neighbor interactions for the spin current model. And C1 is much larger than C2. And we have reproduced the type 1, type 2 cycloids. And we also predict the new cycloids, in particular the 1, -1, -1, which may actually exist. Also, the period of the cycloid in 110 film becomes longer with thinner thickness or higher temperature. Thank you for your attention.
All right, our talk is open for discussion.
It's very interesting. Is there a way to intuitively kind of get a sense of how you would expect different thin film strain fields to couple differently to the nearest neighbor versus second nearest neighbor terms? So for example, you have a 001 versus 110 oriented film, and therefore you have in-plane pinning and out-of-plane relaxed. And is there kind of an intuitive way to think of how the ratio between C1 and C2 would change with these changing biaxial strain fields?
In my understanding, there will be some change, but the general form of this phase diagram may remain similarly. It's just the shift of the boundaries, because around the boundary it means the two magnetic configurations have very close in energy. So by changing the strain, this boundary may shift towards one phase or the other phase.
But I think I'm asking, how does strain move you through this phase space?
Yeah, this is some ongoing work, and I think, for instance, I remember if I increase the tensile strain, it may favor slightly more this 1 - 1 cycloid. So the area for this type 1 cycloid will be smaller, but for compressive strains, the other way around, that the type 1 cycloid may expand a little bit.
But that's assuming hydrostatic-like strain fields, right?
Yeah.
Okay. Thank you.
Actually, can I follow up on that? I'm also curious. So as you change the strain, you can also potentially change the contributions from the other energetic terms, like the short-range exchange and the Dalachinsky-Maria. I mean, this seems like it could get very complex as we start to do strain, because that's what we can do experimentally. So I'm curious what your thoughts are on the other contributions as you make these changes.
Yeah, that's a very good question. Actually, when I just answered the first question, because this is a very heavy calculation, it's about 40,000 because we need to run the molecular dynamics simulation for each pair of C1 and C2. So for the preliminary result, we just change the C1 and C2 and calculate the energy. But in principle, we should relax the structure again and see what's going on, and that would be more accurate.
Yeah, we've seen some things recently where we think under larger strains, the exchange interaction becomes quite important relative to the Dalachinsky-Maria interaction. So yeah, maybe we can talk about it offline, but yeah, it's a really good question.
Okay.
Yeah, go ahead.
I'm sorry, maybe I didn't hear well. Did I understand that C1 and C2 were fitted to some large-scale calculation of the whole effective Hamiltonian? And are there some more direct way how to get from ab initio the estimation of C1 or C2?
These two, we treat them as parameters. So that's why we change C1 and C2 and see which area may give us this good explanation for the experimental result. So they are not fitted by DFT or anything. It's just parameters.
Any other questions for our speaker? Okay, great. Let's thank our speaker one more time.